So the stream should be online now. So can anyone check if it's online?
Yeah. It's online.
Thank you. So where is it? So hello everyone again. This is the second part of my talk, a tour of Common Lisp. So the last time we had a talk in July, so I was a bit interrupted, and so I stopped somewhere around here, but I'm gonna quickly recap what I was talking about. So yeah, we're going to talk about the language itself, not about its ecosystem. This is so Common Lisp is a programmable programming language. It's gradual typed, it's multi-paradigm, it can be both compiled and interpreted. It's well, usually it has automatic memory management. And there are multiple implementations. This is the creator, one of the creators. So it's defined by the ANSI document. Yeah, so the syntax and semantics are interconnected in the sense that so we have this. So it's we have this form, which is basically everything in the language, and it consists of literals, symbols, and lists. And lists can be a form can either be a literal, a symbol, or a list. And then a list can be also either so it can contain symbol. So usually, if it's a language form, it starts with a symbol. And then every other form can follow. So you can see this on the diagram. This is the form that multiplies 4 numbers and then adds the results. So it has a recursive structure. The comments look like this. And we have the quotation semantics that allows us to control evaluation of forms. And so we arrived to basic data types. I think I actually went over that, but it was a bit too quick. But yeah, generally we have symbols, numbers, characters, sequences, hash tables, and structures. And so the symbols are the most important part of the language. They are basically names for things. And there are 2 special symbols, nil and t, which mean, so nil has 2 meanings. It's either a Boolean false or it's an empty list, and t is a Boolean that means true. And there are 4 kinds of numbers, characters that can be written as literals like this. So it's hash, then slash, then the name of the character. Then we have sequences, so it's either conses or arrays, and conses are well, you can say it's the most general form of list in the language, because basically a list is a bunch of conses where so each cons consists of head and tail. So head is we get this by the char operator, and the tail we get by the cadre operator, and the last cons in list is always an empty list, so it's new. And so we also have arrays, which can be n-dimensional, and vectors are a special case of arrays. so one-dimensional arrays, and strings are strings are vectors that consist of characters. And then we also have hash tables and structures like in other languages. So yeah, what we have in the language, let's start with procedural programming. So for procedural programming we have functions which are defined like this. Define, then we list the name of the function, then we have the arguments, and then we have an arbitrary number of other forms as body. Then we can define global variables with def var with the name and the value, which is a form that gets evaluated to the actual value. Then we have local variables that we can define with let. So basically anything that is in the body gets evaluated with the environment that is defined by the pairs within let of names and values. Then we can set the variables with set f, and we can call functions by having a form that is a list that starts with the symbol that denotes our function. So this is a simple example. We define a global variable foo, which we assign 42. Then we define a function called square that multiplies its argument x on itself. Then we call it on our global variable, so sqr foo, which multiplies 42 on 42. Then we change the value of our variable to 3, then we call it again, and we see that the result changed. Then there is a more complex function with 2 arguments and a local variable bar. Then we have, in this case, for the function definition hello, everything that comes after name and age is its body. Then in the body we have this let form, which allows us to define this local variable bar, and then the body of let is this 2 format calls, and format is a function that outputs a string to a stream. Well, in our case the stream is our terminal or REPL. So we define this function, and then we call it with 2 arguments, a string and a number, and it substitutes these templates in the format strings, and we get our output on the bottom. So, but function arguments can be more complex than that. We can have optional arguments. So they go after this special symbol ampersand optional. So everything after that is an optional argument. So in this case we have one mandatory argument, and other ones are functional. So if we call this function with one mandatory argument, it errors out. Then we call it with one argument, it works fine. Then we can call it with our one optional argument, so there are 2 arguments total, it's also fine. But if we only have one mandatory and one optional argument, then it errors out. So then we have the named arguments, so they go after the special symbol ampersand key. So in this case, when we call such a function with named arguments, we need to specify, before we so the actual argument is preceded by its name symbol that starts. So it's a keyword symbol that starts with a column. So in this case, it's our key2, and then after that goes the actual value. Then we can have the default values for both optional and named arguments, which is, so instead of just specifying the name of the argument, we instead specify a list that consists of the name and the optional value, or on default value. Sorry. So then we can have a variable number of arguments with the ampersand rest. So in this case, this special argument would be a list. So then we can have multiple return values of a function. So we can specify a function that returns more than one value, which is not a very common feature in programming languages. So in this case, so in other languages we would usually return a tuple or a list, but in this case we can have, for example, one value. So basically any other value would be optional. So we can the callers can handle only the primary return value and ignore everything else, which can be very useful. And so to return multiple values from a function, we use this form values, and after that we list our each of our optional. So the first one is our usual return value, and then the other ones are basically the additional ones. And we can also just supply them as a list with this values list form. Then we can turn when we call such a function, we can get its multiple return values as a normal list if we want. So it would contain all of the returned values. And we can also use the returned values as local variables. So it's we decompose them in such a way, so it's like let, but instead of these pairs, we use the values that are returned by our function that returns multiple values. But so basically you can think of them as optional return values, really, because that's how they're usually used. So we can put our variables and functions into packages. Other programming languages can call them namespaces. Well, in this case it's an explicit namespace because we also have implicit ones in Common Lisp. For example, we have an implicit namespace for functions, and other Lisp dialects like Scheme don't have that. So in the case of Scheme, they have the same implicit namespace for both variables and functions. But in our case, it's a separate implicit namespace. So when our reader of our Common Lisp implementation, or in other words, a parser, reads a symbol, it gets interned into one of the packages. So it's either the current package or the one that we specify with the colon prefix like this. So package name colon, then symbol name. And we can also avoid turning our symbol into any package with the sharp prefix. And we define our packages like this with diff package. So first the name, then what so we can include other packages into our package. So these symbols from these used packages would be available without a prefix. And then we can also specify what symbols our package exports outside with the export form. And then we can select our current package. When we select our current package, everything in it becomes available without a prefix. So we do this with the in-package form and the name of the package, and the default package is CL user. So we have then I'm going to talk about the control flow. So the conditional expressions were actually invented in the original Lisp back in 1957. So before that there were conditional statements, like in Fortran, I think. But in this case, this conditional is an expression, so it is an expression. It returns a value depending on its first argument. So this is where it was proposed originally by John McCarthy. So yeah, we have conditional expressions. This if form, the first argument is test. It's a predicate. So if it returns t, then it evaluates the argument then and returns its value. And if it's the test is negative, then it evaluates and returns the else argument. And else in this form can be optional. So also then and else are single expressions there. So if we want to have a compound expression there, we have to use a progn form, progn, that would evaluate all of its arguments and return its last expression as the result. And then we also have these special forms, when and unless. So in this case, when is equivalent to if without else. So it returns the body when the test is positive. Otherwise, it just returns nil. And unless. Also the body does not get evaluated if the test is negative. So unless is the same thing, but with the negation of the test. So if the test is negative, then it returns the body, or if the test is positive, then it returns nil. And then we have this cond form. So in this case, it's basically a conditional expression, a compound conditional expression, where depending on which test in this list is correct, it returns the body that corresponds to it. So yeah, this is also useful. Then we have the iteration forms, the infamous loop operator, which is basically a language within a language. So it has a bit of it kinda tries to look a bit more like English. So for example, here we have loop for x in this, then there is this list, then do, and then we print value. So in this case, this particular example of loop, we have the x as the iteration variable. So it goes over this list of 1, 2, 3. So first x would be 1, then it would be 2, and etc. So Then this operator executes whatever comes after do. So in this case, it executes print with the changing x variable. So this whole operator would print 1, 2, and 3 in this case. So it's basically it can have clauses for variable initialization and stepping and value accumulation, termination test. So it can terminate early, unconditional and conditional execution, and other things. So it's a fairly big chunk of the specification, really. And then there are simpler do operators, so we can iterate over a list, we can iterate a certain number of times, and there is this more complex, more general do form where we can specify what variables we iterate on, how they are initialized, how they are incremented or generally changed, and we can set up when our loop stops. So it's not as complex as loop, but it's otherwise it's very general. And we have more basic control flow primitives. So Goto is, as we know, it's considered harmful, but it can be actually useful. For example, when you are writing a compiler, when you really want raw Gotos for your intermediate language, for example. So in this case, we can specify our blocks. So in this case, we can have blocks and tags. So functions and loops are implicit blocks of our control flow. They're implicit blocks, but we can specify parts of our forms as explicit control blocks. We can then return from. We can return from our implicit block as in the loop by calling this form return, and then we can specify the value it would return, or we can return from our function or any other explicit block with return from form, where we specify either the name of the function or the name of our explicit block. And then we have tags, which are basically Goto labels in other languages like C. So we can specify. So first, when we have tags in our code, this part of the code is surrounded by tag body. Then inside tag body, we have these tag symbols, and after each tag symbol comes whatever comes after our label. So a bunch of other forms, for example. And then we can go to each tag by using this form, go, then the name of the tag. And so the tag names are lexically scoped, and you can jump across functions with this, and they unwind stack when you go across them. So then we can also have functional programming style in Common Lisp. So functions are a proper type as well. We can pass them around, we can return them from so functions can return functions. And as I said, this in Common Lisp we have a separate implicit namespace for functions. So this has certain implications for our language, and Lisp dialects that have a separate namespace for functions are called Lisp 2 as opposed to Lisp 1 like Scheme. So yeah, Common Lisp is Lisp 2 in this case, and so we can access this namespace by using symbol function form with the symbol, or this can be abbreviated with the sharp syntax, and we can call our functions explicitly by using this abbreviation in this example. So we can do this with either apply or funcall forms. So apply, in this case, so the argument, we supply arguments as a list. In this case, it's a list literal that contains 4 numbers, or we can simply specify them without a list directly like that in funcall. And we can set the functions. So we have these basically we can set function names in our function namespace with set f, just like normal variables. So in this case, but to access this namespace, we need to use the f definition form, which so this tells to set f that we set a function rather than a variable, and then we can supply our function as a value. In this case, we define bar as full basically, but we can specify functions otherwise. I will show that. So yeah, we can use functions as arguments for other functions. For example, mapCar is a function that applies its argument. So it applies the first argument, or rather the second argument to the first argument. So in this case, it applies this function 1+, which increments its argument to this list. And so when we do that, we return so it returns a list of incremented values in the list. And we have the reduce operation, which basically sums everything in the list. With this function we supplied, we can supply any other function instead of 1+ or plus, whatever we want. So we can, other than specifying functions by names, we can also have anonymous functions and specify them in place. So the original Lisp was inspired by lambda calculus, invented by Alonzo Church. And so the anonymous functions, because of that, are specified by a lambda form. So with lambda, we can specify our function in place, just like normal functions with the arguments and its body. So in this case, previously we supplied the function to mapCar by its name, but in this case, instead of the name, we specify it in place. So we have the same thing, but instead of giving the name, we are just defining the function that increments the value, and we apply it to this list, and we get this incremented list as well. And every function in Common Lisp is a closure, so they capture their environment, or their so there are any variables inside the function that is not in the list of the arguments. It is, so its value gets captured as well. So we can see this in this example. Yeah, this is actually from Symbolics documentation. So this code is a bit outdated, but it works. So in this case, we create a function. So we define a function makeCounter, and this function returns another function that basically increments this local variable count every time we call it. So then we can assign this. So we can call this function makeCounter and assign its returned function to the name C1, and then we call C1 the first time, it returns 1, but then we can call the same function again and it returns 2, because when we called makeCounter, we called this lambda form, and this lambda form, it created a new function, but because there was this count variable in the body of the function, it became enclosed. So in this case, as it was originally defined as 0, so when this function is created, it equals to 0. But yeah, so in this case, we enclosed count in our new function, and every time we call this function again, so this value is preserved, and we can basically increment it that way every time we call it, because it is part of the environment that is contained within this function. So yeah, and then if we make this, if we call the function makeCounter again, we get a completely new function with a different with a separate count value. So we can see that we can do the same thing again with it, and it will again start with 0. So yeah, so every function in Common Lisp is a closure that encloses its lexical variables inside its body.
Don't need the hash symbol and the apostrophe in modern Common Lisp.
Well, it's
you return the lambda.
yeah, it would spew out warnings if you call it in the current Common Lisp implementations, but you can make it work. It's just a simple example I had on my hand, so I decided to use it. But it shows how closures work. So then we can, yeah. So Common Lisp is commonly thought as dynamically typed language, but it's really gradually typed. So we can, so compared to other languages, in Common Lisp, it is values that have types instead of variables. So and it has its own type hierarchy, which you can look up in the specification, and you can extend it with the def type form. I'm not gonna go deeper into that. You get a values type by using the type of form. You can type it. You can check its type dynamically with the check type form. So you give it the value and the type you expect, and if it's not the right type, it would signal that. And then we can also check our types statically at compile time. So to do that, we can actually declare types for variables as well. So with this declaim form, we can specify the type for our variable, and then we specify the name of the variable we want to type. And we can do the same thing for functions. So we can specify the types for its arguments and for its return values. Yeah, so this allows the implementation to first to do error checking at compile time and also do optimizations also at compile time. And not every implementation does that, but the most popular one, Steelbank, Common Lisp, or SBCL, it does that very well. So if you want to make your code faster, you would specify types for things, but it's not necessary. So it's a nice optimization if you really want it, but it's completely optional. So basically typing is optional in Common Lisp, but well, it's static, so the compile time typing is optional, but the types are also always checked dynamically at runtime. So this way the errors are still checked, but it's of course less efficient than checking them at compile time. So if you want to optimize your code, you would specify types this way. So Common Lisp is also an object-oriented language, so it has an object system which actually appeared. So as I said in the first part, Common Lisp was being developed over like 10 years, and there were 3 major revisions before it was finally ratified in ANSYS. So initially Common Lisp didn't have objects, but it was added sometime in 1989 on the second iteration of the language. So it's called Common Lisp Object System, and it was actually the design of this object system was so in its design, so Xerox PARC, the original creators of object-oriented programming as we know it, contributed directly to the design of Common Lisp object system. So it is more similar in spirit to the object system of Smalltalk rather than Java, for example. And so we have objects. They consist of slots or members in other terminologies, and classes define objects, and slots can be shared within a class between members of that class. So we can there is inheritance, of course, but other than this direct inheritance, as in Java, for example, we can, instead of single inheritance as in Java, we can have multiple inheritance. So we can have mixins. So one class can have multiple superclasses. This is used for composition instead of so currently there is this mantra in object-oriented programming that says composition over inheritance, and this is actually very useful for that, because this way you can compose your classes from multiple smaller modular classes, and this works very well. And yeah, so you define classes with the div class form. You supply the name, all are superclasses, and then the slot specifiers. So the slot specifiers start with the slot name. Then we have the name of the slot and its arguments. So we can have, so the arguments can be either the initial. So with the arguments we can specify how this slot is initialized and how we can access it. and there are other options as well, which I'm not gonna into right now. And after we specify the class, we can make an instance of that class with the make instance form like this. So we specify the class with the symbol, and then we can specify the initial values of its slots like this, and then we can access a slot of a class with the slot value form, and we can define all sorts of accessors. And with the class why we need to define classes. So with classes we can define generic functions. So generic functions they specialize on our class hierarchy. So we can so basically in our case objects are nouns and generic functions are verbs. So generic when we define a generic function, instead of this is a bit tricky to explain, but in other languages, object-oriented languages like Java, usually when we have a method of the class, it is always attached to a specific single class. So we don't know if it's not on the slide. So we call it with object dot method. So it's dispatched on this single object. So every method in Java is always tied to some class. But in Common Lisp there is no such restriction. So in Common Lisp we can define our generic function, and then this generic function can be specialized on its arguments. So we can so this basically methods are specializations of our generic functions. So for example, here we define our generic function hug with 2 arguments, and then we can specify methods. For example, we can have method that gets executed when A is person and B is person. So person in this case is the class. So in the case, so the first method definition is for the case when both arguments are of the same class, person. Then we can specialize this generic function with another method where we can have so the first argument can be a person, but the second argument can be a cat, for example. And so in this case we create these methods for classes, but they are not so our object system is not really class-centric, it's method-centric. So we need classes to specialize our generic functions like this. I hope I explained it well. So
it's multiple dispatches.
This is called multiple dispatch. So instead of dispatching on a single, so methods are dispatched not on a single class as in Java, but on multiple classes. So methods can be matched in an arbitrary way to more than one class, and so this allows a lot of flexibility in that way. And we can also have there is another feature called method qualifiers, which allows us to not just add these specializations over our classes, but it can also allows us to, so this allows us to hook into our generic functions before, so either before they are executed or after they're executed. And we can also replace them completely, so we can override them as well with certain method definitions. And so there is this whole algorithm for computing the specific generic function for our arguments, and this is what it looks like. I copied this from Common Lisp cookbook. So first we complete all of the applicable methods for our arguments. There is no applicable primary method. We signal an error. We sort them in order of specificity. Then we execute our around method if we have one, so that allows us to override that method, so override our default method completely. Or yeah, this is a bit complicated to go over in an overview, but yeah, so we can, so there is this so generally there is this algorithm which I recommend you to read on your own, but in other words, we can specify our, we can make our generic function specific to classes of our arguments, and we can also hook our methods even further, so we can execute functions before or after our generic functions. So this is very flexible. Yes, so there is also metaprogramming in Common Lisp, which is expressed in many ways. Generally, metaprogramming is extending the language with the means of the language itself. So it's so in other words, Common Lisp is a programmable programming language, and the designers of Common Lisp took a great care to enable this kind of programming. So there are two main ways in which it is expressed in Common Lisp. So first there is Meta Object Protocol, which I think originally appeared in Smalltalk, but it wasn't really formulated as its own thing until Common Lisp with this book, The Art of Meta Object Protocol, by the people from Xerox PARC. So yeah, so this is the definitive source of information about Meta Object Protocol, and I'm not gonna go into much detail in this presentation, but the point is that the object system in Common Lisp is meta-circular, so it is so basically every part of the object system is also a class, and we can extend the object system by extending these system classes. And this allows us to experiment with the object system, to extend it in all sorts of ways. And for example, some people implemented distributed objects that way, so for network programming. So an object can be, so you can do a generic function call on an object that is actually on another machine in the network. Yeah, I think one of such experiments is called netclause. I don't know if it was actually used, but you can find it if you're curious how it is used, how Meta Object Protocol is used for such things. So yeah, and then another major way in which metaprogramming is done in Common Lisp is with macros, and there are three kinds of macros in Common Lisp: symbol macros, reader macros, and macro functions. And macro functions is the main way of doing macros. So macros is so in Common Lisp we have two modes of evaluation, generally compile time and run time. So macros operate really in compile time as opposed to when the program is actually compiled and is running. So they are executed by within the programming language implementation. So macros basically are functions that run on our code, and you can argue that each macro is really a little compiler for our tiny domain-specific language. Well, not really domain-specific necessarily, but yeah, it's basically every macro is a little compiler. And so when our compiler compiles our Common Lisp code, it expands all of our macros. So it transforms our code into its final form by executing these macros, and this expansion is happening within a certain context, within environments where variables can have values, and we can also macro expand our macros explicitly, even when we are using our programming language implementation in an interactive way with these forms, macro expand 1 and macro expand. So macro expand form expands it until it cannot be expanded anymore, and macro expand 1 it does it only once. So it expands the outermost macros basically of the form that is supplied there. So the symbol macros control how symbols are evaluated. So this is one example in this case. So we have a variable things that is a list of 3 symbols, alpha, beta, and gamma, and we define 3 symbol macros for 3 symbols, thing 1, 2, and 3, and we assign that these symbols actually expand to a form that gets one of the values of this list in the variable. And then when we anytime we expand that symbol, we actually evaluate the so that assigned form of the symbol macro. So when we evaluate thing 1, we actually evaluate first things, so we get the first member of that list in the variable, and so on. So basically we override the meaning of our symbol at compile time that way by making it some kind of form that gets evaluated whenever this symbol is evaluated. So yeah, this is so symbol macros control macro expansion of symbols, and then we have reader macros, which control the reader, which is how the Common Lisp's implementation's parser is called in the specification of the language. So basically we can extend the parser of our implementation with these macros. We can plug our own parsing functions, and they are invoked whenever the parser or the reader hits this character we are overriding. So we can implement various things. For example, we can add new literals, like we can I personally implemented my own scheme booleans in my scheme compiler in Common Lisp. So I implemented them directly as a reader macro, and we can have so yeah, Common Lisp is a so the syntax of Common Lisp is generally a prefix, but with the reader macros we can have some parts of our syntax to be infix. So you can see it in this example. So we have this so our reader macros is invoked after sharp I, so everything in these parentheses is in an infix expression. So it looks more like in other programming languages when where there is actually infix arithmetics. So this is pretty cool. And we can also, for example, use reader macros to implement JSON literals directly in our source code. So we can just put some JSON directly in our source code without any sort of intermediary. So you can see it right here in this example. And yeah, the next point is now I'm going to talk about macro functions. And for macro functions, it is important that Common Lisp is a generally homoiconic language, in the sense that its syntax directly corresponds to the data types within the language itself. So as I talked about earlier in the beginning, so our syntax can be directly expressed as literals, as symbols, and as list of literal symbols and other lists. And so the syntax is very uniform, and we can operate on our syntax, on our abstract syntax tree, so to speak, directly. Just like, so everything is basically a list in our language, all of our syntax, and we can operate on it on like any other list. So going back, yes, so we can simply evaluate it directly. So while in other languages, like for example, I don't remember, JavaScript, eval we are given a string to eval, but in Common Lisp we are given a list, a well-formed list like any other list in our programming language, which we can operate on. But yeah, but eval is so this is our explicit evaluation form, and we can run our modified code that way directly, but we usually don't do that. Instead, we have these macro functions which operate on our forms in a more structured way. So the macro functions are enabled by a thing called by quotes and backquotes that I talked about in the first part. So I talked only about quotes, but so quotes can work as templates. So if you look at this example here, we have this list and a list within that, and it consists of 4 symbols, but you can see that things are prefixed here with a tick and backtick. Well, actually, oh, this is actually so there are two different ways to quote things in Common Lisp. I showed earlier the normal, what is it called, a single quote symbol or tick, and there's also a backtick which is called backquote, and you can see that it prefixes this whole list. And then we also have this prefix before the symbol 3, which consists of a comma and an character, and then we have a prefix before the 4 symbol, which is just a comma. So now I'm going to explain what does it all mean. So the backquote is an extended way of quoting things that allows us to make template expressions, and basically it's the same thing, but we can escape the quotation with these additional prefixes. So comma evaluates whatever actually comes after it, so it overrides the quotation and overrides the quotation and evaluates whatever comes after it. So in this case it would evaluate the value of the variable 4 and insert its actual value into our list. And the comma at prefix is a bit more complicated. It doesn't just inserts the value of 3 in our list, but it also splices it into this inner list that consists of 2 and 3. So you can see the expansion below. So let's say we have so we assigned this list of 2 symbols, alpha and beta, to 3, and to 4 we assigned the list that consists of a single symbol, gamma. And then when we evaluate that earlier backquote, we get a new list that looks like this. So as you can see, the 3 was substituted by the contents of the list, alpha and beta, by those symbols, and the symbol 4 was substituted by the value of 4, which is just a list that consists only of 1 symbol, gamma. So this way we can create templates for our expressions, so for our forms in the language, and we can plug these templates into our macro functions, so these templates get expanded by the compiler or by the interpreter. They can be expanded in both kinds of implementation. So in the compiler, that happens during the compilation time. So we can define a special kind of function that actually, so before it actually gets executed, its body first is expanded in the way I specified earlier. And this template form that gets expanded is defined with this backwards syntax, and so we can have this these special functions that basically transform into another expression into another form during the compilation process. And this is very powerful because so all of that, so these templates are not just text substitutions like in other languages, for example C, but when these symbols get replaced, they are actually evaluated with the full power of the language. So they are normal expressions, and they can do whatever we want them to do. So they don't just get replaced with the value of our earlier of the variables we defined earlier, but they can call functions, they can do whatever we want at compilation time. So basically this allows us to define our own programmatic, you can say that you are defining your own compilation paths that way. So your functions become something else, whatever you want. But this has certain caveats. These two caveats. So the first one is that you need to be careful with how things get actually evaluated, in what order during the expansion of your templates in these macro functions. So things can get evaluated more times than you expect. So you have to take that into account when you write your own macros. And then symbols that get generated within these templates, they can shadow symbols outside of the macro function. So there are these name collisions which are prevented in other languages like Scheme with hygienic macros, but so in Common Lisp the macro system is much simpler. It doesn't have hygiene. Instead we can use gensim form to generate randomly named, well, not randomly, there is usually a counter, but it generates a unique name for our templates when we need them. So when we want a symbol, we can generate it on the fly with gensim. And then there is one more facet that is possibly even more important, is that Common Lisp was designed to be an interactive programming language, so it is expressed in multiple ways, and one good article about this is on REPL-driven development by Michael Evans, that explains how Common Lisp is different from other languages in this aspect. So the big thing about Common Lisp is that it is designed for incremental compilation, and all of the major compilers for Common Lisp they support incremental compilation. So you don't have to compile everything in one go. You can compile single functions, and you can also recompile them even when the program is running and they are carefully replaced in the running program. And whenever we recompile our program, we can either recompile the whole file or a single form within this file, like for example a function definition. And every time we recompile anything in our program, the variable values survive, well, if we want them to survive. So if we define a variable, for example, with def_var form, then it survives recompilation. But if we define it with the def parameter form, it gets replaced every time with its argument. So, but generally we can have, so generally variable values survive our recompilations, so we can change our program while it's running without losing its state. So it's this is how we can develop our program interactively. And then another thing is that the specification of the language actually includes various facilities to inspect the state of our program, everything in our environment, what is in our packages or namespaces, whatever is in our variables, what are function definitions, what is our class hierarchy. We can explore that everything with the facilities of the language itself. So it is actually required by the standard for the implementations to provide all these features. And the whole thing is so most of the implementations provide such a thing as read, eval, print loop. So basically we can launch our Common Lisp implementation, and it would we can type our whatever form we want, a function definition or just a single symbol, whatever we want, or a function invocation into our terminal or our repo, and the Common Lisp implementation, either a compiler or an interpreter, will evaluate it on the spot in the currently running memory image. And if it's a compiler, for example, so some implementations can include both a compiler and an interpreter. Some can be only interpreters, and some can be only compilers, but they can still support this read, eval, print loop by taking your input and compiling it on the fly very quickly. Yes, another important thing is that compilation is very fast in Common Lisp, so this is very important for interactivity. So we can recompile everything. We can compile and recompile everything we want very quickly, and this allows us to have interactive implementations that don't include an interpreter, because they can simply compile everything. And one more important thing for this kind of interactive development is that we have conditions, the condition system. So the condition system is basically a more general form of exceptions. Conditions are they are unexpected situations that can be handled by changing the control flow, and so so you can see the life cycle of a condition. So it can be thrown. So we create a condition object and send it up the call stack. Then somewhere up the call stack there is something that can receive this object, and then this part of the code can when we throw this condition, we can specify information that can be then used by the receiver to choose one of the possible ways to resolve this condition. So then this part of the code higher up the call stack can choose one of the possible restarts, and then it can send this choice back down the call stack. So the control flow returns back to the thrower, and then the thrower does whatever the restart was chosen up the stack. And so either the program can be terminated, or one of the variables can be replaced, etc. So this way conditions don't just usually kill the program, but they can also fix things, and the program can continue running without breaking. And the important part of it is that unlike exceptions, conditions don't have to unwind the stack, so that way we can go back to the thrower and do our restart. and but we can also choose to unwind the stack if we want, and this is handled gracefully. And if there is no handler for this particular condition that was installed earlier, then it simply goes all the way up until it hits our development environment, and we can even choose one of the restarts interactively if we want. Yeah, that's the end of the presentation. I think I covered most of the language, at least the most important parts, and so this is it. So do you have any questions?
Just a trivial thing that I noticed, is the output capitalized by default?
Yeah, so the output in Common Lisp is capitalized by default, but this behavior can be overridden if you want.
All symbols are cast to uppercase when they're read by the reader.
Sure.
So you can change that behavior, I think. I actually have to go, but
okay. Thank you.
See you next time.
See you.
So the next question is about, could you just provide any examples from another functional languages for generic functions? Could you please describe, you just suggested an example from Java, how is it implemented for the Lisp? And could you please provide an example, for example, in Haskell or standard domain or another functional by default case?
I'm not very familiar with functional programming languages. Well, I'm familiar with them on the surface level, so I don't think I can really compare them all that well. So, yeah.
Yeah, but for other constructions, they're just strict assignments from, for example, from standard domain to the Lisp. For example, then the let construction, it's almost the same like in the.
Yeah. There are certain parallels. Yeah, let exists in probably in every functional language. So you can also define local variables the same way in OCaml, in Haskell.
But for me, I think that it's impossible to just for Lisp generic functions get the same situation in, for example, in standard domain. It's impossible to do.
Well, I don't really know enough about this, so I can't comment. So.
Will these slides be available?
Oh yeah, of course I will post them in the group. I actually shared them all, the previous version of the slides in the chat.
In the chat, yeah.
Yeah. I'm gonna quickly check if there are any comments anywhere else. Let's see.
How can I be added to the Discord server?
Oh, I will give you the link for it. Yeah. Doesn't look like there are any comments in the chat, but yeah. So.
What are your thoughts on, like, I guess a blunt thing would be, like, what's it useful for in this day and age, given there's only well-established languages, particularly with the old ones you mentioned. I don't like Java or anything, axe the grind about, but why has it survived? This is a straightforward way of asking the question.
Well, I think it's well, one thing it is, so it's one important thing about Common Lisp is that it is very good for rapid prototyping, but then one unique feature of this language is that it also allows to go quite far with optimizing this early prototype to the point where it can be used in production quite well without writing it in another language. So for example, with Python, so Python is also a very nice language to write prototypes in, but the performance for many things is not optimal, and Common Lisp, well, you can, so with the type specifications and other things, you can optimize it so well that it can actually compete with the C code. So, so Common Lisp spans the whole spectrum of development from early prototyping to production. So this is one important thing about it. And another thing that sets it apart is that it is very flexible. It can, you can extend it with basically every new thing that is invented in programming language theory. You can, so someone even, for example, there is one project called Colton that implements a Hindley-Milner type system in Common Lisp. So it makes it more like Haskell, for example. So and the classic example is object orientation. Lisp was probably the second language that adopted objects after Smalltalk. Yeah, so because it's so flexible, people could extend it this way very quickly.
Well, especially with the methods, with that's relevant to that, and also the Smalltalk went to trouble to make everything uber generalized and uber universal. I personally felt they were ridiculous. Well, my measurement for ridiculousness is if I couldn't learn it well, right? But yeah, I was taught Modular 2 actually going back a long time ago.
Oh.
And I was around the time when object orientation came in onto C. But so the guy who taught us, he was from Hungary actually. No, his girlfriend was from Hungary. But he explained that the Xerox PARC folks, they had forgotten it was relevant to this topic, but they had a note about Smalltalk that the definition of a class was the objectification of ness. Now, how helpful is that? So thankfully Module 2 is more my style, I'll be honest, but no, it's interesting because there is Haskell got mentioned there, and there is a lot of Haskell activity which, would surprise, I guess, a lay person, let's say, who judges things differently. Like Haskell is important for the claims about provability, obviously, and so that is what is what's that guy called? Hodgkinson is using for Cardano, for example. For that,
distributed systems like that.
It's a distributed system, but he's using it for all the consensus measures.
Oh yeah, for verification.
Well, for everything, really.
Yeah.
I think my understanding of the politics of it is that, he's very fixed on using Haskell, and other folks in roughly adjacent communities don't feel so strongly about it. So, but yeah, so that's kind of what I'm wondering: is Lisp active in some deployments?
Oh yeah, something I can talk about is so there is this thing called ACL2. So ACL2 is basically so it's a theorem prover that is also implemented as an extension of Common Lisp. So it extends Common Lisp into a theorem prover language, and it allows for both software and hardware verification. Yeah. And it is actually used in every major manufacturer of CPUs. So at Intel, AMD, IBM it's still making processors, Centaur that makes also x86 processors. So ARM.
Hardware verification.
No, I haven't really gotten to that point, but yeah. So it was, for example, back when there was a bug in the first Pentium. So people at AMD used ACL2 to prove that their processor doesn't have the same kind of problem. So yeah, the users are AMD, ARM, Centaur, IBM, Intel, Oracle, and there are other companies. So it is still. So I'm working at Intel, and it is well known that Intel actually uses ACL2 right now to verify hardware. So
Yeah.
and it's also one of the companies that Intel bought. Another publicly known thing is there was a company called Barefoot Networks, and so they were developing network switching chips, and so they had their own chip design tools, and these chip design tools were developed in Common Lisp as well. And they employ at least one well-known. They employed at least one well-known Common Lisp programmer, Ron Garrett, who wrote the famous article that talked about using Lisp at NASA GPL. Ron Garrett. So they were absorbed by my employer Intel, and they're still working there. But and then they're still using Common Lisp. But so this is so Intel uses Common Lisp for various things.
Yeah, and so it does make sense that it has access to to very specific objects, and can perform tasks on those objects really rapidly, so and at high volumes.
Yeah, so it can be extended to really operate on formal logic and do verification, and it also can do that very performantly. So it is very flexible. That's the main thing. And at some point, there were companies that made computers that had everything written in Lisp from firmware to operating systems to their compilers, not just for Lisp but for other languages. They had their own expert system development environment. They had graphics software, and so they were doing everything in Lisp, really.
And actually, I think there's still a lot of batch processing that goes on. That would be an interesting thing, because the performance needs would be useful there, you know. Like where you're taking, let's say you're taking for capital markets, for example, Japan closes the market in yen currency, and then they have to notify, or somebody in London cares about what happened overnight, so they farm all that, transfer that across to London. So that sort of stuff might be useful to people, alright, you know, if they can parse that high volumes rapidly.
Can I try to show some practical examples in Lisp and ACL2 for in the case of hardware verification?
Yeah, sure.
So, do you know some optimization procedures for Boolean functions in Lisp or in other frameworks? Do you know about the algorithm which is called Klein-McCluskey algorithm?
No, I'm not.
Okay, it's about the
Klein-McCluskey
algorithm for minimization of Boolean functions, which is quite useful for minimization elements inside the chip. So I'm going to research about this question inside the theory Boolean. Which algorithm is better, or can we do it quickly, and how this connected with the VHDL and Variable?
Sounds an interesting question, all right.
Yeah. So, but what's the plan for the next meetup? For the next meetup, what is the plan?
Well, if you can prepare your presentation, that would be awesome, because so I wanted to finish my talk first, but well, it's finished now, and I don't think we have currently anything else planned, so it would be great if you have that for the next meetup.
Okay, great. Thank you.
Probably be in mid-September.
Hmm?
The next meetup, mid-September.
Yeah, around that time.
Yeah.
So, what do you think about the formal verification in So, is it well?
See, well, first I'm not in the computer science. Well, I'm in a computer degree, but I'm not active in that area. But I do know that the only thing that I've seen myself recently is the Haskell stuff. That is, again, it's not obvious to so many people because of all these other commercial distractions. But that's how that sort of stuff is being handled in this specific cryptocurrency, and even there. Like they want to kind of, I mean, I know somebody who teaches this topic, but yeah, even there they want to de-risk it for lack of programmers, right? So there's a lot, and this is why it's interesting that Lisp even survived, because well, obviously we know the history. If we're here, I guess we know that Java exists. So I didn't invent it, as they say, but and C succeeded to an extent to do the object-oriented thing, even though again you could say nobody asked it to accept trends, employment trends and all that. But yeah, so it's just interesting to see what's unique about this in terms of like why people move away from it or anything else.
Oh, it was
That's a very good answer though, to show that it like you were nervous about using the word domain specific in your talk, but I mean it's a good reason to keep it up. If it outperforms everything else, that's that, and it does something that's controllable and controlled, and like it's tricky, but at least it has a real purpose then,
Yeah,
So-
originally it was most commonly used for artificial intelligence, as you know, but because of the last AI winter, so it really affected the whole.
That's kind of what
Yeah.
I'm interested in. Yeah, well,
Yeah.
true. You could say,
This
Actually, I saw a talk McCarthy was giving. I can put it into the meetup. Just he gave a talk to the UK government. Now they're hardly the exemplars of anything these days, but at the time they thought they were. So that was influential because he didn't convince them. And the guy chairing, well-intentioned, like I mean, I could have been me more or less, but like they differed anyway in what was a sensible use of the of AI as it was then. And the big phrase this guy had picked up in the political meetings, in the House of Commons, whatever, was the combinatorial explosion.
mm,
So he was obsessed about the idea that the numbers could never be processed by a von Neumann computer or whatever, right? So he's like, we're not going to go down the route of neural networks, and we're not going to go into more biology related research, and they funded that then. So the British lost out. That's a bit of a sidebar, but no, thanks for that. I remember, in fact, when you were talking, I was thinking it must have been on what would you call them? Not just floppy disks, but the 5 1/4 inch floppies, single sided. I think probably that you would have had to load into your. In fact, it might even have been luggable laptops at the time. So your screen, you could take a machine and sit it on a desk, and it was like about the size of the amp mixing desk thing you have there. And
yeah.
that was a little, probably, I don't know, 640k RAM laptop. Probably cost about, the equivalent of about 200k now, basically. But so yeah, we would have used Lisp for that at the time. But it didn't. Yeah, it was again consistent to your point. Like it was mostly seen as a pretty cool text processor, which wasn't a frivolous thing though, because like text process. Firstly, as we know with LLMs now, text processing can get trendy all of a sudden, right? If sufficient things happen there. But like it wasn't trivial because you didn't have any text processing much. You had word processors, for example, in the kind of common business software. The course I was doing mostly was about office automation, as they call it. So like you didn't have the processing power to do word check and stuff like that. That's taken for granted. So the efficiencies around things like conditional compilation, like you said, for example, explicitly in your talk, something isn't compiled if it's, if it doesn't, you had an if clause at the very top of the talk, if an if clause isn't going to be compiled at all, if it doesn't evaluate to anything, whereas you can turn that on off in a lot of compilers. And compilers go on, in case people don't know, at least my understanding is compilers basically morphed into language translation, like natural language translation software, which again is...
There were some research was adjacent into grammars and such for parsing.
Because exactly, so and I think that would be kind of interesting in a sense, like in people are considering what to do, like in the longer run, because it'll be easier to convince people that if you use the language, the height that we're living through now, right, which I think it's already a year into it practically, obviously people will settle a bit about it, but like I think that if you are in the context of looking for research grants and stuff like Tim Berners-Lee had to do years ago, it could be very interesting just to explain that it's got to do with natural language processing and translation and all that stuff. A quick point about Tim Berners-Lee. He was so he had the idea of the internet basically, and
the World Wide Web.
World Wide Web, correct? Yeah. So, and because the internet existed, so he wanted to explain like hypertext links would be useful for people bumping to each other in the corridor and so on and all this. So he wrote up that, and they just ignored it. He ignored his paper, discussion document. So he submitted the same paper. It shows how the usefulness of polymorphism and all. So he submitted the same paper repeatedly and just changed the title each time, each iteration, sent the same message. Eventually somebody picked it up as well. So if you're in the situation having to look for funding for stuff, I think it probably is very interesting to say that it has power to deal with natural language as well, and solves problems that are extant around that area, which could be very interesting stuff.
Yeah, actually, there was an interesting talk on the topic of possibly solving the problems in artificial intelligence with new programming languages. So it was called Artificial Intelligence, a problem of plumbing. Yeah, this talk by Jerry Sussman, who was one of the original people who worked on Lisp and who created the famous MIT course on programming. So, yeah, I think.
Susskind, isn't it?
Jerry Sussman. Susskind is his colleague, I think, who worked on physics stuff. Yes.
He co-authored a book on structure and interpretation of classical mechanics.
Yeah.
And there was one structure interpretation of computer programs.
Oh yes.
Which is Hal Abelson and Jerry Sussman.
Yeah, so this
Susskind is in Stanford. Leonard Susskind. He's different. He's not related to them.
Yeah, so I recommend watching this talk. It's very interesting, and it really touches on the idea of possibly extending the programming language in such a way that it could in extending programming in such a way that would enable solving the problem of creating a more general kind of artificial intelligence.
Well, I think that's kind of implied by what I was saying, that people who have more money than sense, basically, capitalists, right? Let's put it like that. So they, and organizations like universities, like they'll basically be be interested in doing something, because what will happen, I think, is that the stuff we're seeing now hyped up will run into performance.
It's already running into them.
And so, aside from the kind of like what I might call dumbness of like what it currently does, really, I mean, I avoided it for as long as I could, but I did use Bing there, the chat, the GTP part of Bing. So like, basically, it just is a script to walk through Wikipedia, and I mean, it's totally trivial, really. I used to work for Oracle at one stage, and one of the things that Larry Ellison was keen on, and he's not such a fool as people might think, but so this is going back, I guess, 7 years, and at least 7 years. Well, let's say 7 exactly, I think. Pre-lockdown, but yeah, probably 7 years. And he his thing was he built the in-memory database, which is a good idea, clearly. And his way to show it off in expositions and all that was take a lot of tennis information from, no, he took all of the information on Wikipedia and ported it up to a computer, right? So then you can parse that, you know, and analyze it. His exemplar was a tennis player, Rafael Nadal, I think was a tennis player. But like the point is that all of Wikipedia is in your RAM now. What are you going to do with that? Now, again, it shows how little appetite there is for really cool stuff out in the world, you could say, because yeah, you could do really cool stuff in Wikipedia if you want, and that's 5-7 years ago. Sitting in one RAM instance, you know, on an on-premise machine, whether it's cloud or not, beside the point. But so like, there's a lot of solved problems that I think people will start to reevaluate how useful those things are, and there'll be pressure to do something better.
There was a professor, Patrick Winston at MIT. He has the best course on AI, and he had written using Lisp, I think. He had written this piece of software which you give. So what he did was he took Shakespearean plays and put that, and it would evaluate and summarize it for you, but summarize not in ways which is just a jumble of words. That makes sense. That like it would tell that yes, this character won.
There's a thematic side to it, like
yeah, that was actually very nice, and he didn't use anything like ChatGPT or anything.
Yeah, but
it was brilliant.
This is I mean, again, like, well, I can justify it by saying that the words are up on the screen there, right? Talking about this topic. But I mean, like I did a degree in Trinity in almost exactly, well, yeah, what are we, 20 years ago, I suppose. Yeah, 20 years ago I was in the ticket. And so like that meant that even then you had Microsoft Word, if you were to write up, like part of the course material would be, you know, writing up papers, like writing documentation, because we did law and we did some other stuff. So like if you were to write up, let's say you were to write up a paper on copyright, software piracy or whatever topic, or peer-to-peer was one thing we had to write up on. Peer-to-peer was pretty hit back then. And so you were to write up that and say your thoughts on the likely evolution of peer-to-peer or whatever. And you've got a constraint that's supposed to be handed to the tutor in, let's say, just 700 words, right? And if I had borrowed stuff or whatever, mashed together, I might have had a draft that was like 1,500 words from cut and pasting stuff together. So like my job is, and I'm in a hurry, I've got a day job as well. So like my task is make this fit into 700 words and be somewhat articulate. But even then, 20 years ago, Microsoft Word had click, if you knew to navigate the tools up, and click, summarize, and it made the length you required. You know, computers were magical even back then. You know, so like that's another reason that the appetite for this will dissipate pretty fast. Like I would think, but if people are interested in getting projects started up, it's a good time for looking at things that optimize that sort of thing. So it's been great.
I have to go.
Yeah, it's actually it's about time to finish anyway. So 8:30 p.m. So I need to see you.
Take care.
Thank you.